Okay, Assalamualaikum warahmatullahi wabarakatuh and good day. So today we continue on the stress and deformation in cylinder. So our subtopic for today is on the 10.3, the pressurized effects. So actually this section present the thin wall and also the thick wall cylinder with internal and external pressurization. Is mean this time we are going to learn about the two conditions. One is the thin walled cylinder and also thick walled cylinder, which exerted by the internal and external pressurization. So the material in this section is used for a wide range of application. For example, the pressure vessel loaded with the internally or externally. The second one, the storage tank. Third, the gun barrel. Four, hydraulic and pneumatic cylinder. Fifth, transmission pipelines. Six, machine elements such as rolling element bearing, race or gear press into shaft. But remember, you must differentiate between the thin wall cylinder and thick wall cylinder. But how? Okay, so the question is, based on this book, the cylinder inner diameter represented by DI is 40 times larger than its thickness TH. So then it will consider as thin wall. However, in other situation, if the smaller radial ratio of the cylinder inner diameter to the thickness, so the analysis is considered as a thick wall. So actually this criterion is actually like arbitrary. So actually it depends on what accuracy that we want in the stress analysis. But actually it's a good guideline. So in the mathematically we can say that when the inner diameter divided with the thickness, then we get the value bigger than 40, then we consider it as a thin wall cylinder. However, when the inner diameter divided with the thickness and the value is less than 40, then we consider it as a thick wall cylinder. So here is we have showed the abbreviation where Ti is a cylinder inner diameter, while Th is a cylinder thickness. So then we continue to 10.3, 10.1 thin wall cylinder. Alright, so right now we go to look what is thin wall cylinder. So in figure 10.a here show a thin wall cylinder subjected to the internal pressure. So the internal pressure here, this Pi is represent the internal pressure. It is assumed that the pressure distribution is uniform throughout the thickness. Okay, this assumption is very important because it's applied to the thin wall cylinder. So for the thin wall cylinder, the stress consider uniform throughout their thickness. So the radial stress is more relative to the circumferential stress because the when we thickness cylinder thickness divided with the inner diameter, so we see what inner diameter is less than 1. Therefore, a small element can be considered to be in plane with stress with the principal stress shown in figure 10.1b. So when we want to calculate this stress, actually we take this small element here and then we draw like this. So we have sigma 1 for the first stress, sigma 2 the second stress which part in the axis of z. The sigma 1 is on the theta z. Another one is the radial axis. So okay, we have here, okay, this is the length. So for figure 10.2, this one is the front view of the cylinder shown in figure 0.1a. Actually this is the front view. So figure 10.1 is the front view from this figure. It shows that force acting on the small element, this is the small element, due to the internal pressure. So Pi is the internal pressure, Rho is the outer radius, Ri is the inner radius of the cylinder, Th is the thickness of the cylinder, this is the theta, the angle. Okay, this element also has a length of dl. So here is the DL. So this element, DL is over here actually, around this here, in the thickness direction. So the theta component of the stress is called the tangential stress or hoop stress. So hoop stress, or the sigma 1 equivalent to sigma tangential, is equivalent to internal stress times radius. Here radius actually, when we refer to the book, is actually the internal radius divided with the thickness. So this one is the first stress. We got the value over here. Then another one is the average axial tensile stress. We call it as a longitudinal stress. Sigma is represented by sigma 2. Here is the location parallel to the axis Z. So also called the sigma Z, the stress in the Z axis. So equivalent to the P internal stress times the radius of internal radius divided with 2 times the thickness. So this another one, the stress in the radial direction is from the equilibrium. The stress from radial is equivalent to P, the pressure. However, the pressure is usually much smaller as compared to the tangential stress and also the stress in the z-axis. So we found out that the radial stress equivalent to 0. So it is a reasonable approximation. So we found that the stress 3 equivalent to the stress radial equivalent to 0. Remember that the circumferential hoop stress sigma theta is twice bigger than the axial stress sigma z. In summary, for the principal stress for the thin wall cylinder, we represent by 3 formula. We have the first one, the hoop stress sigma 1, and the longitudinal stress represented by sigma 2, and also the stress in the radial direction sigma 3. So these 3 stress is related for the thin wall cylinder. Next, for the example, let me see the example how we're going to calculate in the thin wall cylinder. Example 10.2. So given a 10 mm inner diameter cylinder made of a material with a yield strength of 400 megapascal is subjected to an internal pressure of 2 megapascal. Use safety factor of 3 and assume that thin wall analysis is adequate. So you need to determine the wall thickness required to prevent yielding based on A, maximum stress shear stress theory MSST, B, by distortion energy theory. So the solution is based off from the equation 10.8 to 10.10. We have the stress 1, stress 2. We substitute the value into the formula. This is internal pressure, this is the inner radius, and divided with the thickness. So we obtain the value. We're still looking for the thickness over here, right? So the sigma 3 equivalent to 0, because of we know that sigma 1, the stress 1 is bigger than stress 2 and the stress 2 is bigger than stress 3. The principal stress are ordered properly according to the equation 2.18 in the chapter 2. So to solve using the maximum shear stress theory MSST based on equation 6.8, yielding occur according to the MSST when sigma 1 minus sigma 3 equivalent to the yield strength of the material divided with the safety factor based on equation 6.8 actually. So we substitute stress 1 and stress 2, and solving for the thickness, we get the thickness equivalent to equation of internal pressure times the inner radius times the safety factor divided by the yield strength of the material. So we get that 0.75 millimeter of the thickness. While for the von Mises stress, So note that in this case that we know that second stress equivalent to stress 1 divided with 2. So the volumetric stress for the biaxial stress state in the obtained from the, we can obtain from the equation 6.1 as sigma A stress E equivalent to this equation, and we substitute with the sigma 1. So we find out the yielding occur at the equivalent to yield strength of the material divided with the safety factor. So we found that when we substitute the value, it occurs at 0.650 millimeter lower than the first solution. So let's you try for another example. This one you have to do it. The exercise 10.2, the thin wall cylinder. Given a 9 mm gun barrel bore made of a single piece of 4140 chromium molybdenum, QNT 425 degrees Celsius is subjected to an internal pressure of 249 megapascal. Use a safety factor of 2.5 and assume that thin wall analysis is adequate. So you need to determine the wall thickness required to prevent yielding based on maximum shear stress theory (MSST) and distortion energy theory (DET). Based on both findings, discuss your finding and give your opinion. So remember that then you need to submit your answer to the ITEL and check their due date also. And another question, you have question 10.1, 10.5, 10.6 and 10.7. Also, you need to submit to the ITEL. Remember, pay attention on the due date. Okay, thank you.